Okay, so I'd like to begin by thanking the conference chairs and the senior program committee for the award. It was certainly very unexpected, but a very nice surprise. So this talk, as the chair mentioned, follows on from my invited talk on Tuesday, where I mentioned the hospital's residence problem, which has applications to junior doctor allocation. What I'm going to focus on in this talk is the case of couples who are pairs of residents who want to become matched to hospitals that are geographically close to one another. In that setting, a stable matching need not exist. So what can we do to try and cope with that complexity? We can try to find a matching that is as close to stable as possible. That's what this talk is all about. The problem of finding a matching that is as stable as possible is NP hard. So we're contributing some constraint programming and integer programming models. I'm going to describe those in terms of just an overview and then give an indication of our experimental results that we've applied to random instances. So this is joint work with Ian McBride and James Trimble. Ian has moved on to pastures new, and James unfortunately had to go back to Glasgow yesterday, so can't be here. So let's just begin with a recap briefly of the hospital's residence problem, which models the assignment of junior doctors to hospitals. So we have a bunch of residents, R1 up to RN1, and a set of hospitals, H1 up to HN2. And each hospital has an upper bound on the maximum number of residents that it can be assigned to. Residents and hospitals rank one another in strict order of preference, and we say that a resident R finds hospital H acceptable if that hospital appears on that resident's preference list, and unacceptable otherwise. So a matching is just an assignment of residents to hospitals that satisfies the following three conditions. We never match up a resident to a hospital that he or she doesn't want to go to. We never multiply assign a resident to more than one hospital, and we never give a hospital more residents than it has room for. Now, Roth argued that what we really want to aim for in a two-sided matching market with preferences on both sides, such as this, is a stable matching. And there are many matching schemes around the world which produce stable matchings of residents to hospitals, such as the National Resident Matching Program in the United States. But the main focus here is on couples. That's the case for the classical problem. But when we have couples, we're modeling the situation where pairs of residents apply jointly so as to be matched to hospitals that are close to one another geographically. A couple's preference list is typically of the form HPHQ, a series of pairs of the form HPHQ. So we have a couple RIRJ, then a pair such as that on their preference list represents the simultaneous assignment of RI to HP and RJ to HQ. And the intuition is that HP and HQ will be hospitals that are close together. The remaining residents who are not involved in a couple are called single. So there are several stability definitions in the literature for the hospital's residence problem with couples. And the one that I'm going to be adopting in this talk is one that was formulated jointly with Eric McDermott in a previous paper. Stability, regardless of which definition we adopt, is the absence of a blocking pair. And I'm going to give an outline of the definition of a blocking pair in the context of HRC. HRC is the hospital's residence problem with couples. That's the acronym we're going to be using for this problem. Before we get to the definition of a blocking pair, here is an example instance just to show you what a kind of typical problem instance might look like. Here we have 8 residents in total, and we have 8 hospitals. Each hospital just has a capacity of 1 in this little example. Now we've got 2 single residents, R3 and R7, who are applying on their own, and they rank in order of preference individual hospitals. But we've got 3 couples, and R1, R5 are a couple, for example, and they have 2 pairs of hospitals on their preference list. So their joint first choice is for R1 to go to H1 whilst R5 would go to H2. And their second choice is for R1 to go to H3 and simultaneously R5 to go to H6. On the other hand, the hospitals have ranked individual residents in order of preference. So that's just one example of a problem instance. So now I'm going to define a blocking pair. Now, blocking pairs have different flavors depending on who's involved. It might be a single residence involved in a single hospital, or it might be a couple and a pair of hospitals. So the first type of blocking pair is the simplest, and this is the same definition as for the hospital's residence case from Tuesday, but let's just remind ourselves of the definition. So we've got a single resident R and a single hospital H, who essentially could improve relative to their situations in the matching. First of all, in order to do that, they have to find one another acceptable. The second condition tells us how the resident could improve, either by taking on hospital H because he was unmatched to begin with, or by rejecting his assigned hospital and taking on H instead, which he or she prefers. And condition 3 tells us how H could simultaneously improve. If H was undersubscribed to begin with, then H improves by taking on an extra resident R. Or if H was full, then it improves as long as it prefers R to its worst assignee. Then it can reject its worst assignee and take on R instead. Here's an example of a type 1 blocking pair. We've just got a small matching shown in red, and R1 and H1 will form a blocking pair. They each prefer one another to their assignments in the matching. Okay, the second type of blocking pair, which is now a new type of blocking pair that we haven't covered already on Tuesday, involves a couple, RI, RJ, and a single hospital HK. And the intuition here is that one of these residents wants to move to HK whilst the other one is happy to stay put. So we've got two subtypes depending on who moves. In subtype A, it's going to be resident RI who wants to move to HK, whereas RJ stays put. So here, M of RI and M of RJ just denote the hospitals that these residents are matched to in the matching. But also the hospital has to cooperate, and hospital HK will cooperate with RI if it prefers RI to one of its assignees who's not RJ, if it turns out that RJ was already assigned to that hospital. The mirror image of this is subtype B, which corresponds to the case where RJ wants to move to HK whilst RI stays put. So let's see an example. This is a blocking pair of type 2A, and here we've got a couple, R1, R2, who are jointly matched to their second choice pair of hospitals. R1 is with H3, whilst R2 is with H2. We've got a single resident R3 matched to H1. Now R1 wants to move to H1, whereas R2 would stay put if they move to their joint first choice. H1, on the other hand, is happy to cooperate because it prefers R1 to its worst assignee. So that's an example of a blocking pair of type 2A. Now we can also have blocking pairs that involve two hospitals as well as a couple. So here's an example of a type 3A blocking pair which involves a couple RI-RJ and two hospitals HKHL on this couple's preference list, such that those two hospitals are distinct and they're not hospitals that either of those residents are already matched to. Now, both of these parties have to improve relative to their situations. So first of all, the couple has to improve. It would improve either by being unassigned to begin with or because it prefers that pair of hospitals to its original assignment. And then also, the two hospitals concerned have to consent to the improvement. They would improve if, for example, HK is undersubscribed or it prefers RI to one of its assignees. And similarly, HL is undersubscribed and prefers RJ to one of its assignees. So here's an example. We've got a couple, R1, R2, who are jointly matched to their second choice pair of hospitals, but they prefer, R1, R2 prefer to be jointly matched to H1, H2. If we look at the two hospitals concerned, they have an incentive to cooperate with that couple. H1 prefers R1 to its worst assignee. H2, on the other hand, is undersubscribed and happy to take on R2. So that's an example of a blocking pair of type 3A. Now, I can go on in this vein by defining the remaining types, but instead I'm just going to skate over these. We've got three remaining types of blocking pair, and these remaining types of blocking pair deal with the possibility that we've got a couple, RI-RJ, and a single hospital HK that they both want to move to. They both want to move to the same hospital. And that hospital HK is not equal to either of the two hospitals that they happen to be matched to already. Now, RI-RJ has to have an incentive to want to move to these two hospitals, but also the hospital has to cooperate with these residents involved in the couple. And it could do that either because it has 2-3 posts already, or it has one vacancy and it can free up another by rejecting a poorer assignee, or if it was fully subscribed and it can free up 2 vacancies by rejecting residents that are worse off than RI and RJ. So again, we can give an example of one of these types of blocking pairs, but in the interests of time, I'm going to move on. And that completes the definition of the different types of blocking pairs for the HRC context. So instead of laboring through the blocking pairs, I'm going to present a stable matching instead. So here is an example of a stable matching, and it's shown in green by circling relevant entries on the preference lists. So why is it stable? Well, we could try and convince ourselves by ruling out the existence of blocking pairs. We could go through every single possible candidate, but I'm just going to look at one potential candidate where R1, R5 wants to move to its joint first choice, H1, H2. Currently, R1 is with H3 and R5 is with H6. The question is, would the pair of hospitals cooperate with that couple? And the answer is no. Although H1 would like to take on R1, the other hospital concerned does not have an incentive to cooperate with R5 because it strictly prefers its current assignment to R5. So there's not going to be a blocking pair involving this couple, and we can also check the remaining parties. They won't be involved in a blocking pair either. Okay, so what we've got is an example instance of hospital's residence problem with couples with a stable matching. What you may remember from Tuesday is that every instance of the classical hospital's residence problem in which we have no couples admits a stable matching. And Gale and Shapley proved that in 1962, and they proved that by giving an algorithm which will always construct a stable matching. But when we have couples involved in a problem instance, a stable matching might not exist. And in the interest of time, I took this example out, but if you're interested, then simply request it at the end if time permits, and I can show you it. What's more, even worse, the problem of deciding whether a stable matching does exist is NP-complete, and that was first shown by Ron in 1986. Even when stable matchings do exist, they can have different sizes, so we might be interested in finding one of maximum size if one exists. So what's some other prior related work on the HRC case? Well, there have been several heuristics in the literature that have been proposed for this problem. One example is the Roth-Paranson algorithm, which has been used for several years in the National Resident Matching Program. So typically what these heuristics do is they run for some time, and we might typically give them some maximum length of time that they can run for. And if they terminate within that time that's been allotted to them, then they will give us a stable matching. But if they don't terminate, then we can't be sure whether a stable matching exists or not. And there are several other heuristics as well. Biro et al. In a paper in 2011 examined their heuristic, which they called algorithm C, and they showed with an empirical evaluation that there's a high likelihood that this algorithm will terminate with a stable matching if the proportion of couples is low compared to the total number of residents, which is likely to be satisfied in practice. There are several integer programming models that have been given in the literature. One ourselves a couple of years ago in the SEA conference will find a maximum stable matching if one exists, or report that none does. Drummond et al. Last year again came up with an IP model, but their stability definition is slightly different to ours. And finally, Oliver Hinder proposed an integer programming model for the case where all hospitals have capacity 1. So it doesn't include all the types of blocking pair definitions that we're including here. Drummond et al. Also proposed a SAT encoding for the problem, again relative to their slightly different stability definition. And I also want to highlight a quite remarkable result that was proved a couple of years ago by Nguyen and Vochra, and they showed that we're never too far away from a solvable instance of HRC, because if we take our instance and we allow ourselves to perturb the capacity of each hospital up or down by at most 4, and introduce at most 9 new posts, then we can always reach a solvable instance, which is a quite amazing result. But what's the focus of this work? It's all about most stable matchings, which is to try to cope with the possible non-existence of a stable matching. We've seen that a stable matching might not exist, so what can we do about it? Well, we can try to get a matching that is as close to being stable as possible. So how to define this? Well, let's suppose that M is a matching in an instance of HRC. We're going to denote by BP of M the set of blocking pairs of this matching. So if the matching is stable, then BP of M is the empty set. Now, different matchings can have different numbers of blocking pairs. And here's an example instance of HRC where we can show matchings where we have 2 blocking pairs and another one which just has a single one. So let's see this matching here, which matches up the 2 couples. And we've got a blocking pair involving single resident R3 and another one involving R6. So a total of 2 blocking pairs. So we could say that that's not as good as this matching, in which we match up the 2 single residents to their first choices, and we get a blocking pair involving the couple R1, R2. The other couple does not block, so we just have a single blocking pair. And there's no stable matching here, so we might regard this one as being the most stable one we can achieve. So formally, we define a matching M to be a most stable matching if its number of blocking pairs is minimum taken over all matchings in the instance. And we regard these matchings as being as stable as possible. That's our measure of instability, the number of blocking pairs that the matching admits. So we denote by min BPHRC the problem of finding a matching with the minimum number of blocking pairs, a most stable matching. So from our SEA paper a couple of years ago, it was already known that this problem is NP hard because even deciding whether a matching with 0 blocking pairs exists is NP complete. And the problem was shown to be NP hard in this restricted setting here, even if there are no single residents, even if each preference list of the remaining parties are short, and even if each hospital has a capacity of 1. But one of our new results in the present paper is to show another case in which this problem is NP hard. Namely, even if each couple finds only a single hospital pair acceptable, and again, each hospital has a capacity of 1. Not only that, the problem is hard to approximate in the sense that there's no approximation algorithm with a performance guarantee of n to the 1 minus epsilon for any epsilon greater than 0 unless p equals np, where n is the number of residents. We also have a positive result, a special case of a problem which does turn out to be solvable in polynomial time, where each single residence list is of length at most 2, each couple's list is of length 1, and each hospital's list is of length at most 2. Now, you might consider that this is not a particularly practical case, but what this result does do is it helps us to narrow down the boundary between the polynomial time solvability and NP hardness cases. That's for the case where preference lists are bounded, but what about the general case? So we have an IP model for this problem, and it's based on the following variables and constraints. Now, I'm certainly not going to have enough time to talk through this model in any level of detail, so let's just give a very brief overview. The variables are binary valued, and for every resident Ri and for every position P on Ri's preference list, we have a variable xip, which is equal to 1 if and only if Ri has his pth choice hospital. And we also have a binary valued variable theta I, p, which is equal to 1 if and only if Ri is involved in a blocking pair with the hospital at position P on his list. We also have a special variable for each resident Ri to denote the possibility that Ri is unmatched. So what about the constraints? Well, a simple set of constraints can enforce a matching property. We've also got one constraint family per type of blocking pair. And these constraints actually allow us to have blocking pairs, but at the expense of a contribution of 1 to one of these theta I, p variables. So then if we just count up the total of the theta I, p variables, then that gives us the number of blocking pairs. And our primary objective is then to minimize that total. As far as the secondary objective is concerned, we might want to maximize the cardinality of the matching, subject to finding a most stable matching. So this IP model was implemented in Java and solved using Cplex. And now I'm going to turn to the constraint programming model, and again, just give a brief overview. The idea is somewhat similar to the IP model in which we have analogous variables, but we've also got some additional ones which help us with modeling. And again, there are analogous constraints in that there are constraints per blocking pair types, but this time the model is actually more concise because the description is more flexible due to the fact that we're not constrained to have integer linear inequalities. This model was implemented using Minizinc and solved using the Chuft solver. And we also employed a pre-solve strategy which was specific to this problem. And for values of k, where k began at 0 and iterated through 1, 2, and upwards, we searched for a matching with at most k blocking pairs. So k was fixed, and in the knowledge that any solution must have at most k blocking pairs, we were able to cut down and apply some reductions to the model size. The reason this worked well was because the maximum number of blocking pairs admitted by any of these optimal solutions was always very small, as I'm going to show you in the experimental evaluation, which is right here. So the experimental evaluation that we did was based on generating a large number of random instances of the problem. And what we were varying were numbers of residents involved in a couple, numbers of hospitals, and the lengths of the residents' preference lists. And we generated instances to take into account the fact that some hospitals were more popular than others, and the same for residents. We measured various things: the time taken to solve to optimality, the size of an optimal matching, and the number of blocking pairs in an optimal solution. For each data point in the charts, we averaged over 1,000 instances for each parameter value. We had 4 experiments in total, The first one, we varied the number of residents. The second one, we varied the number of couples, keeping the number of residents as 100. The third one, we varied the number of hospitals, keeping the total number of posts as 100. And the fourth one, we varied the lengths of the preference lists. So here are the results from the first experiment. We've got, for example, the mean time taken to solve to optimality, which increased with the number of residents for unsolvable instances. The time taken to solve unsolvable instances, which were instances that did not admit a stable matching, was always far more significant. The size of the most stable matching increased with an increase in the number of residents, and the number of blocking pairs was never more than 1. With experiment 2, as the number of couples increased, again, the problem was more difficult to solve. The size of a most stable matching decreased as the number of couples increased, and again, the number of blocking pairs was never more than 1. For experiment 3, all I will highlight here is that the maximum number of blocking pairs actually went up to 2 in this particular case. So there were some families where we actually had a slightly larger number of blocking pairs. And finally, for experiment 4, again, there was never more than 1 blocking pair that we encountered there. The problem got more difficult to solve in terms of the time taken as the preference list length increased. Very brief comparison between the integer and constraint programming models, focusing on the bottom set of charts. This focuses on the unsolvable instances, which were again the more difficult ones to solve. The curve here with the pluses represents the time taken for the integer programming model. The curve at the bottom with the circles is the time taken for the constraint programming model with pre-solve. So the constraint programming model with pre-solve was definitely the winner in all cases. So final slide to conclude with some of the main messages from the experiments. We never found more than 2 blocking pairs among all of the experiments that we did. The constraint programming model was faster than the integer programming model with problem-specific pre-solve turned off. It should be mentioned that integer programming has its own pre-solve, but not the problem-specific one that we were doing for constraint programming. On the other hand, when we had pre-solve switched on for constraint programming, it was over 8 times faster than integer programming. So for future work, for a fair comparison, we should also do this problem-specific pre-solve for integer programming and compare the performance. We'd also like to investigate larger instance sizes, for example, to see whether the model can cope with the Scottish Foundation allocation scheme size of instances. We'd like to see if there's again a trend regarding the maximum number of blocking pairs admitted by an optimal solution. To get the scale up, we'd like to consider refined constraint programming models, which again could involve techniques such as variable and value ordering heuristics, and for integer programming we could apply branch and price, for example. So that's it. Thank you very much.
Thank you, David.